Hello, everyone. I hope everybody is happy and fine. Today, we want to talk about exponential relations. Exponential relations are relations whose equations are in the form of y equals b to the exponent of x. So b raised to the exponent of x. For example, 2 to the exponent of x, or 1 half raised to the exponent of x, or like 3 or 10 raised to the exponent of x. And this b is called the base of the power, and it has to be positive by definition, but it cannot equal to 1 for an obvious reason, because 1 raised to the exponent of any number would be 1 anyway. So we will not get an exponential relation. Um, the easiest, the simplest, or most basic exponential relation is the one defined by y equals 2 to the exponent of x. The base is 2, the exponent is the variable x. And we always start with table of values. We did this in grade 9 when we were graphing linear relations. In grade 10, we graphed parabolas, quadratic relations. We always started with a table of values. So we do the same thing here. I have selected some x values from -3 to +3. And I have y equals 2 to the exponent of x. And I'm going to evaluate the value of y for different values of x. If x is 3, I start from the bottom. 2 raised to the exponent of 3, or in other words, 2 cubed, is going to be 8. So the answer is going to be 8. 2 squared is going to be 4. And then 2 to the exponent of 1 is just 2. And 2 to the exponent of 0, if you recall, we learned in the first part of this unit, when we were reviewing exponent laws, we learned that any number raised to the exponent of 0 is equal to 1. So 2 is not an exception. So 2 to the exponent of 0 is going to be 1. And then 2 to the exponent of -1, using the negative exponent law, would be 1 over 2 to the exponent of +1. So if you have something like 2 to the exponent of -1, because right now x is -1, and you want to calculate y. If you have 2 to the exponent of -1, that is 1 over 2 to the exponent of +1, or in other words, 1 half, right? So this is going to be 0.5 or 1 half. The other one, if x is -2, 2 to the exponent of -2 would be 1 over 2 raised to the exponent of +2. In other words, 1 over 4. And that is, of course, a quarter, 0.25. It's a quarter. And then if the exponent is -3, we will end up with 2 to the exponent of -3, which is 1 over 2 to the exponent of +3. And that will be like something like 1 over 8. And that is 0.125. Okay, so we are evaluating the values of y for the exponential relation. Needless to say, if you had y equals 2x, which is a linear relation, we did the same thing in grade 9. We had different values for x. We plugged in for x. We found the value of y. For example, 2 times 3 is 6. 2 times 2 is 4. 2 times 1 is 2. 0. And then if x is -1, 2 times -1 is -2. And then we have -4. If x is -3, 2 times -3 is -6, and so on and so forth. This is the same thing we did in grade 9. In grade 10, we did the same thing with quadratic relations. So we grabbed the x values, we squared them. So 3 squared is 9, 2 squared is 4, 1 squared is 1, 0. Negative numbers, if you square them, because negative times negative is positive, the outcome is going to be positive. So table of values are very clear. And this was, of course, linear relation, if you remember from grade 9. And this other one is called quadratic relation from grade 10. You studied it for the first time. And now this new one is called exponential relation. That's the third one we are learning. And the variable x is in the exponent part of the power. Okay, so now that we have the table of values, just like we had it in past years, why don't we just plot them and try to come up with the graph of this so-called exponential relation. So 3 and 8, I start from here. This is 3 and 8 would be right there. And then 2 and 4 will be this other point. 1 and 2 is right here. 0 and 1 would be right there on the y-axis, -2. X is -1, y is 0.5, which is about here, If x is -2, a quarter is the y value, and 0.125, which is very close to the x-axis. So now that we have plotted 1, 2, 3, 4, 5, 6, 7 points, we will draw a smooth curve passing through these points. So we do our best to draw a smooth curve passing through these points to see what kind of graph we will end up with. Definitely it's not a parabola, definitely it's not a straight line, and it's a parabola that is not a parabola, it's a curve that is very steep on the right side. It rapidly increases. So this is the shape of the exponential relation graph. Y equals 2 to the exponent of x. I label it. And about the properties of this exponential relation, we can say the following. If you remember, in linear relations, we used to find first finite differences. We used to add a column here, and we used to subtract the y coordinates to see what differences we end up with. So bottom minus top, -4 minus 6 was a 2, -2 minus 4 was a 2, 0 minus 2 is a 2, 2 minus 0 is a 2, 4 minus 2, 6 minus 4, all of these were 2. So if you remember, we said that if you end up with the same number top to bottom, the same constant, in this case 2, if that happens in the first finite difference column, which is nothing but the differences between the y coordinates, then in that case, we call that a relation linear, and the graph was a straight line. Now, in case of quadratic relation, it was not like this. So when you find the first differences, 4 minus 9 is -5, 1 minus 4 is -3, then -1, then 1, then 3, 9 minus 4 is a 5. So you see that they're not the same number top to bottom as they were in linear relations. So we say, okay, why don't we find the second finite differences? So we did this last year. So we went -3 minus 5, which is a 2, -1 minus 3, that's a 2. Bottom number minus top, 1 minus 1, that's a 2. So when you do that, 5 minus 3 is a 2. You see that this time you end up with the same constant top to bottom. And we said that in these kind of relations where the second finite differences are all the same for successive x values, these relations are known as quadratic relations. Y equals x squared was a quadratic relation. The graph was the basic parabola. And in case of linear relations, the first finite differences were all the same. But now that is not the case for exponential relations. You clearly see here, if I subtract 4 from 8, 8 minus 4 is going to be -4. Or no, 8 minus 4 is going to be +4. And then 4 minus 2 is going to be 2. And then 2 minus 1 is going to be 1. 1 minus 0.5 is going to be 0.5. So we see that there's absolutely no relationship between those differences that we end up with. But instead, something else is happening here, something interesting, and that is the ratio of successive y values are the same, believe it or not. Now, you might have noticed already that 8 is double the 4, 4 is double the 2, 2 is double the 1, 1 is double the 0.5, and so on and so forth. So this tells us that the ratio of successive y values are the same, believe it or not, for exponential relations. So, for example, if I divide the 0.125 by 0.25, we end up with 1/2. If you divide 0.25 a quarter by 0.5, that's going to be 1/2 again. If you divide 0.5 by 1, it's going to be 1/2 again. 1 divided by 2, it's 1/2 again. 2 divided by 4 is 1/2 again. 4 divided by 8 is 1/2 again. As you clearly see, the relationship here in between these successive y values is that the ratio of these y values are the same. In other words, 8 is double the 4, 4 is double the 2, 2 is double the 1, and there's no relationship like those other relations we studied in the past with respect to the differences between the y values. So this is the property of exponential relations, that the ratio of successive y values are all the same. we saw the graph how it looked like. So if I look at y equals 2 to the x, if I want to mention some properties, I would say, first of all, the y-intercept is at 1. So maybe I can write here y-intercept is equal to 1. And in fact, whatever the base be, it doesn't matter. Base could be 3, could be 10, could be 2. When you raise that base to the exponent of 0, you end up with 1 anyway, because any number raised to the exponent of 0 is 1. So this y-intercept is always going to be this number 1 here. So even if that's like 3 to the x or 10 to the x, or even 1/2 raised to the exponent of x, which can be written, by the way, with a negative exponent, the y-intercept is going to be 1 anyway. All right, so the y-intercept in any case is equal to 1. And about the x-intercept, what I can say is that the graph becomes extremely close to the x-axis on the left-hand side. If x becomes like -3, -4, -10, -100, -10,000, as x becomes smaller and smaller and smaller, the value of y becomes very, very close to 0, but still positive above the x-axis. So it doesn't touch the x-axis. The curve does not touch the x-axis. As a result, we don't have any x-intercept. It's not your fault. So x-intercept, I would say none. There is no x-intercept. Same thing for the other exponential relation whose base is 1/2. Okay, then what else can we say? This line, by the way, this x-axis, where the graph approaches but never touches, has a name. We call it an asymptote. So we call this horizontal asymptote. An asymptote is just a line. It could be vertical, horizontal, or even slant. In this case, it's a horizontal asymptote, and that's a line that the curve is sort of attached to it, because as the curve approaches the line, the distance between the curve and the line, this so-called asymptote, becomes smaller and smaller and smaller. So basically, the curve approaches this line but never touches it. This is called horizontal asymptote, and in this case, if you want to find the equation of the horizontal asymptote, it would be just the equation of x-axis, which is a horizontal line, and the equation is y equals 0. Basically, equation of the x-axis. Same thing is true for the other exponential relation. So that's what we can say about y-intercept, x-intercept, and the equation of horizontal asymptote. Another thing we can say here is that the graph is almost horizontal on the left, but it's rapidly increasing on the right. So I can say here, as x increases, y rapidly increases. So from basically left to right. That's one thing we can say. See what happened here? We went from 1 to 2, 2 to 3, okay? But then all of a sudden from 2 to 4, and then 4 to 8. Next one will be 16. Next one will be 32 all of a sudden. After 32, we get 64. It gets very large very quickly. After 64, it becomes 128, and then 256, and then 512, and then 1024, and then 2048, and it keeps going very, very fast. So as x increases, y rapidly increases from left to right. But on the left side, when x is decreasing, so I say as x decreases, we see that the graph becomes almost horizontal. So I should say the graph is almost horizontal. That's what we can say. And the value of y actually approaches 0. Okay, and we can say and y values approach 0 because they become smaller and smaller. Okay, so this is what is happening to this exponential relation. So linear relations, quadratic relations, and exponential relations, we saw the differences. In terms of the equations, The exponent of x is 2 in quadratic relations. The exponent of x is 1 in linear relations. And in exponential relations, the exponent itself is the x. So we have some other number like 2 or some other base, 3 or 10, raised to the exponent of x. So this is the differences between them. Now, for the other exponential relation, 1/2 raised to the exponent of x, I could have constructed a table of values here. But if we do, let me do it. Y equals 2 to the exponent of negative x, which is the same as 1/2 to the power of x. If I do that, because of the exponent becomes negative, so whenever I had negative numbers, now the exponent becomes positive, in fact. And whenever the exponent was positive, now it becomes negative because of the negative sign in front of the x. So if x is -3, we have 2 to the exponent of -3. That is 2 to the power of +3, which is 8. So you see that 8 was at the bottom of the chart, but now it's at the top of the chart. If x is -2, 2 to the exponent of -2 would be 2 squared, which is 4. So similarly, we get all these different numbers. So 2 to the exponent of 1 would be just 2. 2 to the exponent of 0 is 1. And then we have 0.5, 0.25, and 0.125. These are the numbers that we used to have at the top of the table of values for 2 to the x. Now they show up in the bottom of the table of values for the other one. So when you plot these points, you end up with scenarios like this. So if x is -1, we have 2. X is -2, we have 4. And when x is -3, we have +8. But in the past, it was the other way. And when you draw these, join the points with a smooth curve, you see that you end up with another sort of exponential graph. And this time, I just quickly label it y equals 2 to the negative x. Or you can say 1/2 raised to the exponent of x is the same thing. So you see that the behavior of the graph did change. So as x increases, this time I can't say y rapidly increases because it's just the other way. So I would say as x increases this time, y becomes almost close to 0, and graph becomes horizontal. I'm just trying to describe what is happening on the right hand side. On the left hand side, of course, I should say as x decreases on the left hand side, on the negative part, we see that y is actually rapidly increasing from right to left. So I would say y rapidly increases from right to left, actually. So I'm just describing what is happening to the graph. And these two graphs are, of course, symmetrical with respect to the y-axis. What else? Yes, and we just have a special name for these kind of exponential relations. When a quantity is increasing rapidly from left to right, we call this exponential growth. Okay, so exponential growth, and whenever the graph is decreasing from left to right, becoming almost 0, we call this exponential decay. So these are two names, exponential growth and exponential decay, that are given to these two different types of exponential relations that have two different behaviors, but at the same time, there's so many things that they have in common, such as not having any x-intercept, such as having the same y-intercept, such as having the same horizontal asymptote. But as you see, one of them is increasing rapidly from left to right. One of them is actually decreasing rapidly from left to right. So one has this particular name of exponential growth. One has exponential decay sort of name. And we will discuss this further in the next lectures. But so far, this much is enough. Please review your textbook, study the related sections, 7.3, 7.4, and we will talk more in future. Thank you.